All right. All right. So, what I want to do now is transition to what we perhaps know now, um, and how it almost fits into those gaps that were left by and this is obviously thinking of the idea of if you in evolution, if you have one missing link and you find it, then you've got two missing links, because you've got the one before and after it. So obviously not this is not the be all and end all. This is a fully open. This is my assumption of filling in the gaps, not at all scientific tested anyway. So and I'm gonna follow the path of accidental panspermia. So the idea that you spoke on before of the idea of us being like celestial rats or like like the idea of that someone has accidentally dropped us
We're
off.
cosmic.
That's
We're
a whole
cosmic feral species. We're cosmic introduced species.
yeah. That is a whole other line of thought that I'm gonna leave, because that's so much more complicated and requires so much more like if this but that. This one I'm gonna go to the simplest,
Well, hang on, hold
most
on. Just
basic.
quick sidebar. So we're not going to talk about the cosmic weeds and the cosmic ferals, but you're going to go down the line of an accidental panspermia. Okay.
Yeah. So, but I'm happy later. Let's go. But just for now, that's the river I'm going to travel down. The river splits, and I'm going to go that river.
All right, sure.
So I want to just for Earth, what is the seed? So the first thing I want to know, what is the seed? Well, what is the simplest version of life? So like what is the prime? So let's go primordial life. You've got a million planets ready for primordial life. What is the simplest primordial life? Um, and one of the, I guess, the interesting things is I've gone through some of the news and the research on what's the simplest version of a self-replicating molecule, and
In
often in these
existence
things
today, you mean?
well, in existence on Earth ever. Probably doesn't exist today other than those extremophiles that live in hot springs and edges of volcanic areas and things like that. But one of the things they found is that the evidence for primordial life they have on Earth says that Earth back then was such a good place for primordial life. And an interest, like one of the interesting things I see that when we search for life today, we're searching for like this somewhere else, like a 21% oxygen with blue oceans.
100%. We have a very chauvinistic and sort of limited view of what life is, for starters, because we can't help it. But secondly, like the Goldilocks zone is what we talk about when we're looking for the perfect planet. And it's a worthy name for the idea, because it's like Goldilocks is going around looking for like the right bowl of porridge and the right bed to sleep in, and that's essentially what humanity's doing. We're looking for another crib somewhere else in space. Like let's be clear here, and we're looking for things that we can eat.
Yes.
And if you look at a lot of the genome research that's going on, it's people trying to patent things that you can eat. Right? That, like, let's be clear that's mostly what we're interested in here. Most of the science being done in the world today is commercial science. It's interested in things that you can profit from. So we're looking for planets that we can profit from. And so we are maybe not thinking about this in quite the right way, and that this sort of Goldilocks fairy tale of what we can find out there is maybe not the right way to think about it.
Yeah. So the idea that like what is a habitable zone? What is a planet? We're looking for habitable for humans, habitable for like for animals that we know, whereas life doesn't necessarily need that. And early, if you could go back 4 billion years and go in a spacecraft and look back at Earth, you'd go not habitable.
4 billion years ago, it was quite a different place, wasn't it? Do you want to just briefly describe it?
Well, 4 billion years ago, I want you to. There's no oxygen. The oceans are filled with caustic. Basically poisonous oceans. There'd be volcanoes going off all the time. The hot springs would be like geysers would be everywhere because the volcanic activity is just way higher. The Earth's so much hotter. The idea of that things afloat, like the solar system isn't like as much as the solar system is kind of a dangerous place now, it's pretty much the meteors are in the same place. There's a band of asteroids, and most of them are there. This is a time where things are whizzing in and out of solar systems constantly, smashing into planets like there's no tomorrow.
So you're saying the Earth's environment locally was quite hostile to what we would imagine as good, worthwhile life. But not only that, the immediate environment was quite hostile as well.
Yeah, and there's literally the moon just collided with the Earth 4 billion years ago. There's other planets that aren't even like settled yet, whizzing into things. The idea of Pluto not being in a regular orbit, because it's eventually, if you took enough time, eventually that's going to whiz into something if it crosses its path enough times. That's the universe, that's the solar system back then. Is things whizzing around, smashing into each other.
It's a pretty gnarly place, and the Earth is pretty gnarly also. Okay.
Yeah, if you went back that long and looked at the Earth, you wouldn't go, man, that's where I'm going to settle. And that's the same planet that we're on today, 4 billion years ago, not habitable. But what would you look for if you were looking for the earlier signs of? If you could go back 4 billion years, what would you look for? So, the evidence that they found is RNA is the most simple molecule. Which is basically a bunch of amino acids which are formed together. And they have heaps of evidence of amino acids being able to form abiotically, so just forming in nature, because it's a nice, convenient thing. So if you have a bunch of types of molecules, phosphorus, carbons, and all that floating around, there's a few nice patterns they like to fall into because they're low energy states.
So I just got to butt in one more time in case we've got any proper sciencey people listening. When you say the simplest molecule, you mean the simplest molecule that could
make itself again?
Yes. Yeah.
Yes. There's two main theories that go on, that is the ones that the geothermal vents, where, in the bottom of oceans, where, minerals and atoms and molecules are spewing out of like lava, hot heated water.
So in other words, don't think about a primordial soup. Think about a primordial volcano.
Yeah, but perhaps that's the one that I want to veer away from, because that's the idea that somehow life made its way to the bottom of an ocean and then like formed there. I think a much more promising origin story for life on this planet is if we go with a theory that is those volcano geysers and hot springs, where it's on the surface and it's got the component and it's connected directly with somewhere where something from another planet could land on it. It doesn't have to land in a specific spot and fall to the bottom of the ocean.
Yeah, exactly. So picture, when Jesus was talking about casting the seeds, right? So this goes back to a very ancient form of agriculture where you literally just got a handful of seeds and you just scattered them on like the ground, and then maybe you shoveled you scooped a bit of soil over the top just to keep them in place, and maybe gave it a bit of a watering, but you weren't like very, very deliberately and carefully planting seeds in neat little rows. You were just kind of throwing them out there. And so these seeds we're not drilling down to the bottom of oceans here. They just need to settle on the surface and find something to live in.
Yeah. So experiments in early Earth conditions, and on asteroids, which is like, not developed by life things. There's been evidence of sugars, bases, phosphates, that they can naturally arise.
Wait a second. Quick question. Is there any water 4 billion years ago?
Yes, there's water.
Okay, cool.
But the water is not the ocean water is not what we think of now. And that's why I think perhaps those geysers are a better play, because one of the things about geysers that makes it a really promising place for life to start is it has like a cyclic effect. The geyser goes off, then it dries out. The cyclic goes off, it dries out.
Yes.
It has that
regularity is the key to life. That's one theory.
So that's the idea. Imagine you're in a science lab and you're doing an experiment. You're going to do cycles of DNA replication or RNA replication.
Or let's go back to the present. Humanity has benefited enormously from the cycles of the tides, the cycles of the moon, obviously related to the tides, the cycles of the sun rising and setting, the cycles of the Earth tilting, and what's the other thing the planet does where it has the orbital perturbation. So in theory, we've benefited from all of these things.
Yeah, so that's the theory that I'm on this journey down the river. I'm going to go into that canal, that these places on the surface of the Earth are having cyclic effects, giving the components that could form a basic life molecule.
Yeah. So picture a geyser, right? And it's doing its thing. It's going off every so often. So maybe an analogy for that is like those tidal zones of life, where like the water comes in, the water goes out, and all sorts of things kind of live in that space where the water goes in and out.
Yeah, and thinking of this, the Goldilocks that you're speaking of, there's also, for life, there needs to be a membrane around it. It needs to be something holding it together so it can make another thing. Otherwise, it's just a bunch of things replicating. And in these early, life places and in modern day, hot springs and things, they've been able to replicate things without initial cause, like the components that make up membranes. So the things that hold the cell together can form those bubbles. A bubble is a very nice way for things to arrange themselves, and they've been able to replicate bubbles of membranes forming,
Now,
and just by
are we
chance.
talking artificially created environments in laboratories?
Well, some of the things that I read was about they took these things that they were doing in laboratories and took them to geysers and just sat them in the geyser, and from there they were able to
So
get it
they
to
literally
form
just took
these.
some ingredients and went to make a cake in the geyser. Nice.
Yeah. Yeah. So it's not, there's no like, oh, if only this was, like this. It's like, here you go. It's making it. Have a look. So I think that makes it a really promising way to start this journey, is that there's something natural that could occur.
So they were
Now,
able to get these things to make sugars. Did you say?
well, yeah, sugars, phosphates, and the bases, which are the three things that make up RNA. In a more complex way, you could say they make up DNA, but obviously DNA takes a.
So what are the three ingredients
It's
of
like,
RNA? Sugar, phosphate, and
and the amino acid bases. So they're like, when you have your amino acids, you've got humans have their amino acids they need to eat, and your body is made up of amino acids and things that it can self-make. But essentially, these are the very basic building blocks of what, say, a protein is, or like what an RNA is. So the things that make up
yeah.
everything
So
in
you mean
us.
to tell me, Jordan, amino acids are not just things that Joe Rogan sells you?
No. Yeah. But yeah, so basically the things that you need to make up something complicated enough to replicate itself. So all the things that can make up that, they can make that in nature or naturally without interference, and also a membrane to go around those things, because obviously a membrane is important to having something that can make more and be ordered.
Okay, so when you say
And
membrane, I'm picturing something like quite sophisticated, but you're saying it could just be something quite simple.
well, essentially just like the basic fats that go like just form a bubble. It's basically a bubble that encases something. It's microscopic. It'd be tiny, but it's just enough that you could accidentally find one of those self-replicating molecules inside the bubble. And the idea of that one of the theories of the most successful way that could exist is basically something that all its code needs to says is make another one of me and do something else. It doesn't even need to say and make a this and make a a structure and make a a self-replicating whatever. It just needs to say make one of me and do one other thing.
Correct. And so
If it's just
when we think about, when a lot of people think about evolution, they've got a lot of very complicated ideas in their mind. Often it's a lot simpler at the basic level than you might imagine. And all that's really needed, in theory, for evolution and mutation and natural selection to occur, all you need is one thing that replicates. That's it.
yeah, and the to go from like what is the most basic amount of things that can tell itself to make itself again is not that complicated. It's only like it's a tiny molecule that says replicate me.
I mean, it's
And
complex compared to one atom of hydrogen, but it's a lot
oh
simpler
yes,
than
yes.
perhaps what you might imagine.
Yes, it's much easier than going, oh, how did a chimpanzee make another chimpanzee from nothing? No, it's just a bunch of molecules that have found their way accidentally to each other that say, make another one of me right next to me, plus do one other thing, and then you've got the start of evolution. But what I want to propose in this journey that we're taking is that the start of this river isn't on Earth. So we've got millions of planets out there that could be in the same primordial state, and the start of this river isn't Earth. The start of this river is another planet ages away, distant time and space, infinitely from our imagination. And we have all it's done is it's made a molecule that says, make me plus another thing. And that's as far as it's got. And the whole planet is covered in these geysers, and the whole planet does this. And then, like the early solar system, very sad story. Things are whizzing around, and boom, hits the side of you. So the things that I'm gonna go down the road of planetary ejection, which is the idea of an asteroid smashing into you and throwing things into space, or a moon smashing into you, and like another planet smashing into you and ejecting millions of meters of
Yeah,
stuff into space,
and just in
rocks.
case you think this sounds far fetched, it is a far more common occurrence in the cosmos than we originally thought. Is that right?
Yeah, well, I'm gonna start I'm gonna go down the river one step at a time. So we've got planetary ejection, which is what does it take to go into space, and what does it take to get back into a planet? So we've got shock pressures. There's a limit on shock pressure, and there's a limit on how fast something can go into a planet before it combusts. They've got that at here's just some numbers that 3 meters per second, or 3 megameters per second, apologies, and 6 gigameters per second cubed. So they're like shock pressures that basically go from one Kelvin to 1,000 Kelvin.
Well, and
But
those, yeah, I was going to say that's a pretty big range.
yeah, but basically from that, it's not that hard. I'm going to look at that in a second. But within the range, those are acceptable numbers that could get life in or out of a planet, or those molecules in or out of a planet. It's within an acceptable range. It's not. It doesn't need to be floating down on a feather. It can pretty much barrel into a planet and probably be fine.
So we're not talking about the reintroduction of Apollo 13 into the Earth's atmosphere here. It's slightly more robust, the parameters.
Yeah, yeah. A rock that's cubic meters big that just has a few of these molecules in it barreling into the planet.
At 3 megameters per second, is that what it was?
Well, I'll get to. I have another paper that tells me that more specific what the number. I'm just
3 megameters. I'm trying to translate that into kilometers per hour, and I just can't do it. Do you happen to have the figure?
Well, it goes shock pressure is probably better, but so this is gigapascals, 5 to 55 gigapascals. That's a more maybe a more understandable.
How many pascals do I have in my bike tube?
Oh, I don't know.
I think it's like 70 kPa. It's like 70,000 70,000 pascals in my bike tube. And so how many are we talking shock pressure for entering?
The minimum of that's like a few thousand of that. But I mean, your bike tube is nothing.
Yeah.
If you said go fall from space in a bike tube, I'd be like, yeah, thanks.
Yeah.
So there is another one that I just want to just put out there. I don't necessarily want to use this as the but there is another idea of things that if you're in a geyser, you're getting shot up into space. Just naturally things just go out of geysers. And one of the ways that we've been able to investigate the properties of other moons in the solar system is to fly satellites by them and like capture the mist of the geysers. So
sick. I was going to say, like, I'm picturing a geyser shooting some life or self-replicating molecules into the air, but then of course my immediate objection to that is, but wait a minute, what about gravity? Aren't they just going to come down again? But wait a minute, here comes a friendly passing meteor and it's skimming through the atmosphere, right near the surface of this planet without getting sucked into orbit. Is that what we're picturing?
Yeah, so a meteor just flies by a planet or moon. It could even be a moon that has some early primordial soup that shoots into the sky, and it just gets collected on the way out.
Hitchhiker's Guide to the Galaxy. Nice.
Yeah, that's not the river we're going to go down. But I just want to say that's a very adjacent river, if that makes sense. So, but what I want to is that once they're in space. So let's see, the different ways they can get in space is that one of the ones that I think is the most we can picture it is the asteroid that smashed into the Earth when dinosaurs were around. Most of us have a pretty good grasp of what that was like for Earth. So
and also it's the opposite of starting life. We think of it as ending life.
Yeah. So there's a theory that's going around that if we find life on Mars, well, perhaps we just found life that transported from, say, the time of the dinosaurs in a expulsion event from the Earth, where the meteor hit the Earth and shot all of the debris into space. And this basically says that it's basically guaranteed with the amount of material that went into space that we will, because we found Mars asteroids on Earth all the time. It's one of, there is a lot of evidence of Mars. Like, I mean, it's not a lot, but it's a numerous amount of Mars asteroids.
Well, actually, Jordan, let me just stop you. It is a lot, because when you think about the amount of rocks we could be picking up and analyzing, it's a vast number, right? And so to think about the amount of geology we've done compared to the amount of planet there is, and then to have already, out of the very small sample compared to how big the planet is and how many rocks it's got in it, we've managed to find ones from Mars. So it actually is a high rate.
Yeah, and I mean most of it goes into the ocean, which is probably better in a sense.
Yeah.
This is going. There is some trains of thought that going into the ocean is actually worse for early life, whereas landing in these geysers and these freshwater pools is better.
Well, because we're picturing the Earth's oceans as such as pretty inhospitable by today's standards.
Yes, very caustic.
But what have we got so
place
far?
where
We've got things that might have landed on Mars and things that might have come from Mars to us. Okay, we've got rocks flying around everywhere.
Yeah. So just to even to talk of that in this solar system, if we find life on another planet, the chances that we can say that life started on that planet is actually really low because of the amount of material that Earth has shot out, and we know life is here.
I'm so glad you say that. So one of the key features of evolution and the construction of biological life through replicating molecules, from my understanding as a non-biologist, is that evolution is very conservative, is how Richard Dawkins put it in one of his books. So the idea is that nature doesn't want to do things a million times over if it can just do it once. And so you don't want to you don't want to have to explain it coming about twice when you can do with once.
Yeah, and so on this is they estimate that 360,000 large rocks went to Mars from historical Earth impacts, which is a damn lot.
That is a lot.
Yeah, it only takes a small amount of these self-replicating molecules to make it to another planet before, there was once only one self-replicating molecule on Earth, or, but that's formed all of the life today. That could have happened many times, but there's one that's formed all of us.
Absolutely. So that's right. So when we talk about these things, we need to keep the idea of robustness and conservatism in mind, that the ideas we have should have as few if-thens as possible. And for example, my more immediate area of expertise is anthropology, and I didn't spend a lot of time looking at, forensic and physical anthropology, i.e. The fossil record on humans and hominids in general, but I do know a little bit about it. And so you may be aware that two of the dominant theories are out of Africa and dual origins theory. Now, dual origins theory, as it turns out, is quite popular in East Asia, and it comes up from time to time that some academy in China or wherever has said, oh, no, there were definitely dual origins. What is dual origins? Oh, well, basically that humans evolved twice. Now, just on the face of it, apparently there is a little bit of evidence to support this, a little bit. But it's ridiculous on the face of it, if you ask me. To explain humans arising once is a bit of a difficulty, let alone twice.
Yeah, and the idea that I won't dive into that, but yeah, I feel where you're coming from on that. But they've got 70 billion kilograms of rocks went into space 70 billion kilograms of rocks just from Earth when we got hit with an asteroid. And I'm talking about a planet covered in life that was before us, billions of years ago. That shot maybe even more life into space. So only a few have to reach each solar system, because if it gets on Earth, it's going to get to the rest of the solar system. So all it has to do is get to a solar system, and then the whole solar system is going to be contaminated eventually. So they put the odds at 50-50 that life on Mars is pretty much just life on Earth, continued on from a little journey across a little bit of space.
Yeah, which is a fascinating little thing, because I'm old enough to remember, Jordan, this might be a bit distant for you, but you may remember it being in the news. Basically, when we started sending, the more advanced probes to Mars to actually land on the surface and go around, sort of that adventure started about 20 years ago. And so we've sort of had a generation now of lander probes on Mars. And one of the things they kept telling us was, don't get too excited if we find evidence of life, because it could just be contamination from the Earth.
Yeah. Yeah. So from that, I want to take the next step down the river. The next paddle is that let's just assume that I'm going to go with the safer option. Then I'm going to go for the more outrageous option. Is that how could life get from our solar system to another solar system? And I want you to imagine our solar system just being a solar system to a next one. Now, there's something called the Oort cloud, which is essentially, if you imagine the solar system as a nice little bunch of planets, well, you're wrong. There's a whole ton of stuff whizzing around outside of that. That's just, it takes hundreds of millions of years to get around the Earth. It's really far away. But every once in a while, a bit of that comes into our nice little safe zone in the middle and goes in and out. So you might know that's where comets originate. That's where the far distant asteroids that could smash an Earth every couple of 100,000 years. That's where they originate. But the interesting thing about that is it's actually really huge, that cloud. And the thing is that this is think of a geological timescale of billions of years. That every 50,000 years, a star passes within the Oort cloud. So every 50,000 years, a different star comes within our cloud. So our cloud and their cloud combined to mix things. So things that could have been ejected from Earth or ejected from a planet can get, every 50,000 years, we have a chance to hand off. Here's a bit of life, or here's a bit of whatever.
Yeah, well, that's crazy, because I remember reading somewhere or hearing in a podcast, a sciencey thing about how often, basically how often solar systems went through each other. Like in the history of everything, like it may have happened quite a lot of times. And so this is quite exciting. So this is our Oort cloud, which is a relatively local to us, but as you say, also friggin' ginormous. And then other suns going through it, carrying all their planets with them.
Yeah, yes, everything with them. And some of, because this is an interesting area of research, because if you want to know what the early solar system had or what early Earth had, just go and find some evidence out there. You could find bits of Earth from the collision of the moon out there that haven't been that are identically chemically to the day they were smashed, because they were smashed out there. So the reason that we've investigated this is that there's a star called Schultz star, which is 70,000 years ago, was the most recent star to go through our Oort cloud.
It's extremely recent.
So we might have even handed off life. I mean, 70,000 years ago, that's nothing, literally nothing.
Oh no, it's less than a blink of an eye.
Yeah, and think that, so every 50,000, even if you just went back to, say, the dinosaurs, which is like hundreds of millions of years.
So a foreign sun had been through the Oort cloud hundreds of times since the dinosaurs.
Yeah. So we have, if the dinosaur, and this is such a small event in the history of the universe, that if we've sent light, we know that the Earth was covered in life at that time, because obviously there was dinosaurs on the damn thing. We've sent as parts of life to hundreds of different Oort clouds around hundreds of different stars just within our planet, and where our planet's like nothing in the the scope of things. So if our one planet can do it hundreds of times, let's imagine hundreds of planets doing it hundreds of times and passing it across.
Yeah. So actually the interseeding of, as in the seeding going this way, not just coming to us, but going away from us as well, coming from us and coming to us. And picture, there's just an incredible amount of this going on.
Yeah. We don't, in our time scale, we're in a nice little safe spot of the universe or the galaxy, but we're actually just like whizzing around past everyone all the time. No one's going the same rate. We're going 100,000 kilometers an hour in a direction. Well, you only got to go a few different kilometers an hour, and eventually you'll pass by. After millions of years.
It's incredible. But it's making me feel dizzy thinking about it.
So they've got the suspicion is 20 stars will pass within a couple of light years of us just in a million years. So that's not much. A million years is like nothing, and they've got 700 stars will go within 15 light years of our solar system in the next 15 years. So if you think about the transferring of everything, 700 stars could be infected with Earth's galactic expunging of dinosaur, in that short amount of time.
Oh man, that's a lot. And there I was thinking that humans were making huge problems down here, spreading species around everywhere by accident all the time. Well, it turns out we might be doing it all over the joint.
Yeah. But one of the things I want to go down. So that was the small river I wanted to go down, where that's like we're handballing things to the next person and they're getting it, but it's really slow. What I want to go down the river of is a much more violent river, which is what happens if a planet explodes, and it's like going fast. We've gone from like whole, handing, to the next person. Now we're going to go boom and send it. So one of the most interesting that I think that people don't know about our solar system is that we're like a third generation star, which means that there's been a star, it's formed, it's had a solar system, it's had its whole life, and it's exploded. Then from that remnant, another thing's formed, it's had its whole life, and then it's exploded. So, and we could even be more, but we're at least a third. And you can tell that by the composition of our Earth, our sun, what colors it's burning, what it's made up of.
So the star has novaed and then recomposed at least twice.
Yeah, and the amount of distance would have been traveled from just one star having one nova that could send life into space is astronomical. Like that, now we're getting across galaxies. If you put a rock, if you put a rock next to the sun and exploded the sun, that parts of that rock will make other galaxies by now. So now we're talking about properly getting across the universe. So what kind of scale could that happen? Well, if you think about just the Earth, but I'm going to go back to early universe, which is not at all like ours, where suns evolved a lot quicker. If life just forms around and the universe is a lot smaller back then, a lot smaller by an infinite, expanding universe, but what the first galaxies were more closer together. You could more quickly send an exploding supernova of life from one galaxy to another, 4 billion years into the universe rather than 12 billion years into the universe. So that's the river I want to go down on that thing. So pretty much that's my hypothesis I'm gonna present of the idea of,
I think this is fertile territory because it sounds like there's an absolutely prodigious amount of interceding going on potentially.
So so that's where I've gone with modern information. How could you connect those ancient ideas? That's what I've come up with. That we have, here's a system that's not too out of the realm of possibility for things to be transported from one place to another place. Over a million years.
We've definitely gotten around the difficult problem of how it's getting from here to there. That's right, or from there to here.
Yeah. So now this is the bit where we're going to stray away from the what's kind of hard and fast, and go into perhaps a bit more grey area in terms of
more speculative territory.